some new a functionality I added to Calcite last year about streaming and more specifically for event time, time semantics. This presentation might be shorter than I expected, so let's see. So first of all, before go to the event time semantics, there, maybe it's not a formal name, but let's see, there's a processing time semantics. So as another thing. So processing time is the time when the system sees the data. So suppose you have a computer engine, and then you read a data or keep reading data from Kafka. So when you see the data, actually that's your time. So in this case, data is often processed as just deltas, like you buffer data in, for example, every 5 minutes. Then you apply something on this data, and then process this data, and then keep doing that. So this is a way to do streaming, right? So for example, use the Calcite query as an example. You can do select stream, start from orders table, and do a filter where units greater than 3. So then in each, this query likely will keep reading the data and then apply this algebra to in every 5 minutes, and then every 5 minutes there will be new data actually processed and then output, right? So that's pretty natural. So even timestamp semantics actually means that we expect there's a true event happen time in the data itself, or somehow be told by the maybe messenger system. So this is different from processing time, where the data actually, when data is generated, sending to some message queue, and then when the data are processed by the computing engine. So there's a lag between when the data is happened and then and when the data is being seen by the computer engine. So it could be sometimes saved as a metadata, or sometimes it's even as a part of field in the elements or in the messages. Here is just an example. In the order table, maybe there's when each row of this order table is inserted or generated, there will be all the ID, there will be units, probably there will also be a timestamp, say, hey, when this order is generated. So then then maybe this table's data is being sent through network to somewhere to do the further processing, and then there will be a 2-dimension of the time concepts. One is the time, the events happen time, which is in this table. Another is when the system actually receives this data, right? It could be 1 day later, or even several seconds later, depends on what kind of queue you are using, and then the latency of the queue and the arc, lots of lag settings, and like how frequent the computer engine pull the data from the queue, or it's like even the push model, which may be much faster than pull. Okay, so if we go back, so the even timestamp semantic really requires the query we are grouping or drawn based on the event time rather than the time when the system sees the data. This is what is different from processing time semantic. Like one example is when you say I want to know the sum of the loss yesterday. One way to interpret that is in yesterday I have a job, I have a stream job, I keep receiving data in yesterday as our time, and the end of yesterday your job give you a result. So this is one way to interpret that, which is literally more like a processing time. During that day, maybe the data not only when those loss happens, they may not really happen in yesterday. depends based on their event timestamp. They may happen far before yesterday because there could be lag somewhere. And then another way to interpret that is when you keep receiving data from yesterday, even today, and when you see there, when you see event timestamp from based on the data, some data actually happens based on the event timestamp as in yesterday. So you only compute the loss based on from those data. So that's actually what event timestamp semantic care about. And in this case, if based on the example, there are actually probably three problem we care about for this semantics. The first thing is data completeness. So recall that right now when we see a data, we will need to check its event timestamp. Then, which means there could be a lag, and the lag could be large. So use the example. I want to know yesterday's loss, but even now I may still can receive the events happening in yesterday, but maybe delayed during sending through the network, and maybe even in the near future we could still see those kind of data. So there's a question about, hey, when the data are complete, because this is streaming, we never know when the data will show up because we keep reading the data. And second, so okay, to do with the completeness, the better way is buffering, of course, because you literally need to keep buffering data until you believe the data is already all in the buffer. Then you do a sum, for example. Then it introduced the cost problem. So the more time you buffer, the more resource from the memory, computer memory you are using. So literally the cost will increase. So there could be a trade-off between completeness and cost for sure. No, maybe lower cost means less completeness. High completeness maybe means high cost. Of course, it depends on your business logic and the implementation. Lastly, is a additional recurrent problem which you can call the latency. So think about it. So we have proposed a buffer solution to maintain the cost and the completeness. So we want to keep buffering data to a bucket for yesterday's loss. So very common that where you keep buffering, where you believe the data could still show up, you want to see some early results, right? You can give a partially incomplete data from the buffer. So that's way we can think this problem is a latency problem, such that you can control how frequently you can see some result, even early result from the buffer. So yeah, that's just some background about this semantic. And I guess the goal when we write streaming SQL is to try to also consider such problem, even from the SQL perspective. So how to literally let SQL also support and also let SQL provide tools, ways, syntax to allow you tuning between these three dimensions. And there will be never really a perfect answer for this. So probably sometimes the goal of these three dimensions, they have conflicts, right? If you want high completeness, you maybe have to afford high cost, something like that. So although I guess people usually want high completeness, low cost, maybe frequent latency, but sometimes the goal is conflicted. So you have manually sometimes need to specify your goal. You want to optimize for which dimensions, and literally means that other dimension could be satisfied. And yeah, and probably we hope at least at this moment until this slide, we hope SQL probably can offer similar thing to allow us control this dimension. Okay. Yeah. So by the way, before you go next slide, so even without considering the syntax we were introducing in the following slides, even based on the processing semantic, as long as there's a metadata field which indicates the event timestamp in the data, you could still use SQL to grouping based on the event timestamp. But that actually requires lots of work. Like you probably that means you have to manage your own buffer. Then when you see the data, you don't use the processing time to think about that. You check the event timestamp, you buffer those data in your buffer. So then the syntax or the new things introduced in the following slides were most likely rarely means that we're trying to propose a way directly in Calcite level, so you don't need to maintain your own buffer. You don't need to grouping based on a specific field by yourself. So this concept is latency cost completeness hidden and in the Calcite directory. You can use the SQL directory to tuning this rather than use some intermediate DB to maintain a state and then keep updating the state, then doing something like that. Okay, so for such even time semantic, there's the very common API is doing windowing over such timestamp. There are some common types. There are tumble window, fixed windowing. There are hop window, sliding windowing. There are session window. Usually it means per case sessionization. And sometimes there are custom windows to satisfy some special needs. So for even time semantics, we also want applying such window, but we want generate window based on even timestamp first. So make sure even right now I see a data, but the even timestamp tell me it's happening yesterday, so it should go to the window in yesterday. And if the window type is interval window, so literally it's a fixed length window. So it sometimes it should have the window start and window end. Yeah. There could be other types of window. For example, you only have window start, but then the end is unlimited. So that's maybe not really a type of interval. Yeah. So those are maybe more specific window. Maybe some use case need those. But when the window is interval, it's supposed to have window start, window end. Calcite are already supporting grouping window functions. Yeah, until this slides. If you I thought I have here is the syntax actually. So it allows you to select window start, window end from order table and group by a window function. And it doesn't match its streaming aggregation over windows. So it where the tumble hop session, these functions actually help you group by your elements, your data directly into a window. It's sometimes you can think of there's a such function generates a bunch of key for each window, then data goes to each window. It's a grouping, and then you can add the aggregation function in the select here. So literally, it will apply the aggregation function within each window, because group by is literally group by window ID or window key, and then it also offers two like helper function to give you access to for each window what's a window start, what's a window end. Maybe this order. Okay. However, I guess there are some drawbacks from my perspective. We people don't agree. And so first of all, it's not friendly to window joins without aggregation. So if people only want to join and they want a window as well. So the Calcite treating window as a grouping operation, which is true for aggregation. But when you want to do joins, you don't need a group by. Yeah, if you don't want to do aggregation. And if you still want to use this group by stare window function to do join, you probably need to write some verbose query, like you do select and start from others, group by this window. So and then have a join with another group by query, even though actually two group by is only the way to generate window ID, but you are now doing aggregation. So it's a bit verbose. If it would be nice if you can directly do a join without this group by, right? You do some select star from table A, join on table B, but somehow you tell these two query are window query. Yeah. Okay. The second drawback maybe still my perspective is it offers to sort of magic functions. So literally, it says when you use group by tumble, for example, you will be able to use window start, window end in the select. So I feel like it's not that natural to think as a way of secure, maybe. Yeah, and maybe there are even some drawbacks. So the and the others, even though group by tumble hop session can do windowing, at least there's no mechanism to control when to emit accumulated result. So aggregation over windows is still accumulation, and in terms of even timestamp, semantic, we need a sort of buffering to help us increase the data completeness, and then then when to emit the result for the buffering. In the processing time context, it's easy. You just keep emit in every XX time. Usually it's emit per delta, depends on how frequently you fetch the delta, and and we need a way for even timestamp semantic for that. Yeah, and the following idea actually all come from this paper. Credits to the authors of this paper. Yeah, and if you interested, you can read this. Then I just go over what really happened based on the paper idea in Calcite. So first of all, we acknowledge that even timestamp or potentially window metadata like window starts and window end can be a part of the table. So it will be treated explicitly as a part of the data. Use the order ID as an example. Order table as an example. We will keep the even timestamp in the table. We will also likely keep the window metadata as a single field if it's a row struct, or we separate those as window start, window end as two fields. If there are even more metadata about a window, maybe when a result file triggered from window, is it the first one, last one? It says that the triggered from when window is considered as closed. We probably can add more fields or eventually use a struct to represent the window metadata. So then it is different from the previous that the window metadata are accessed by window start and window end as two functions. So I guess the benefits here is that it could be extensible. If there's a more window metadata, probably we add fields to the data. We add new fields to the data table directly rather than adding to support to a new function, or to the window metadata struct if it's a struct. And then we consider to introduce table function to do the windowing. So this is a new syntax to do the tumble windowing. You can do select star from table from tumble, and you give the table data as an input parameter and a descriptor to specify which is your even timestamp field, and give the parameter for the tumble. Literally says, hey, create a fixed 5 minutes fixed window. So what this does, assuming the table data is this table, order ID, even timestamp this as this time, and the tumble table function, the input is a table, output is a table. It will output a table in which it append the metadata to the table, to the input table. So it's like a transform. You read the transform, you feed the table into the transform. The transform will apply the windowing on the table, and then it output another table which contains the window metadata already. And then after this, you can do the aggregation and the join, maybe union based on the window metadata as it's already in the data. So I feel like it's more natural to at this moment to think about after the table function, you get a new table, you have the new case there to identify windows. Then when you want to do based on the window doing the grouping, you just use this new case to do the grouping. And for the join is the same. You no longer need to group, use to group by to generate this window start, window end. After this, table function, then you just join based on this window method. Yeah. So yeah. So now and with the table function, aggregation over window still works. After the table function, you got the window metadata. Then we want to do the per window grouping. You group by window start or window end or both, depends on your need. Join does not require group by syntax. Yeah, because we don't need use group by to generate the window metadata. We use table function. So the join will become very similar to select star from table A, join select star from table B, where table A and table B, they are two table functions. Luckily, table function allows you to define more complex window strategy, because the table function's input is a table, output is a table. So conceptually, the table function can say all the content of the table, of the input table. Then it can do arbitrary, 1 to n, n to n, n to 1, or whatever m to n, changes to generate window ID for those elements. This is highly, customizable. Yeah. Okay. Something I haven't done. So to do. So Emit syntax. So Emit syntax is the idea from the paper that we add the emit clause after the query to indicate when we want to how we want to control the latency and the cost and the data completeness from the table function. Remember in the past example, we see, hey, in the event timestamp semantic word, you actually have built a sort of buffer. Right now, the buffer is actually in the tumble function. And if you, for example, if you want to see a more complete data, probably you have to specify by the emit, right? So say, hey, right now it's the emit after watermark. So maybe you can say, hey, emit, when the data is complete, just say something. And then this would be the way to control at least control the behavior of this table function. So emit could, since it's to do, it's not, really finalized. So there's some question mark here, emit what? Just example, I'm not saying it's going to be implemented, just some example conceptually. So you can emit count xx, which means that, when the tumble function say xx number of, rows, do a emit, literally tumble will give a result. And then as the downstream operator, like, the aggregation and join can start work. And maybe it can say emit allow later data access minutes, say, when you believe when the query believes the data for window is complete. And but data, there's a lag. There could be still data in that window appears after the window is closed. So if those are considered late data, maybe we still have a way to allow the late data be be used to refund the previous emit the result. And of course, you can do emit every xx minutes. Maybe it will be similar to processing time semantic, where you keep give the result after xx time. But this is for event time semantic. Okay, another to do restrictions. Yeah, queries over continuous data may need retracting previous results if emitting or the result happen emitting happens more than once. One example is in the window functions, if after the window functions there's the auto join, right? So when the emit controls the window function to give an early result, because it's auto joins, there could be none emitted for some non-matching case from two sets. But later, because data comes in continuous there, maybe some previous emitted result actually now should be refined as none now, because one set has a row, another set in the past it does not have that, but now that row appears. In this case, we probably need restrictions to tell downstream the previous result now is invalid. Please undo that one, and then redo my current emitted one, because the current one tells the truth. I mean, more closer to the truth. with non-truth. And another example is aggregation. Aggregation, if you do the inverse, there are frequently an example of count frequent that you for each word in a article you count how many times the word appear. If you do an inverse count frequent, literally you give the the for appear once words, there's a list, how many words appear once, how many words appear second, right? So for such cases, aggregation, if it emit an early result, it probably emit word like my name Ray appears once in the article. Then later, after a new my name appear somehow in a streaming way, you need to move this my name to frequency 2 list, right? In this case, the aggregation key actually changed because new data appear. So in this case, you also need retraction. So later you have to do undo, say, hey, remove 3 from frequency 1 list, and then add 3 to frequency 2 list. So in this case, retraction will also needed. The retraction, the need for retraction is because 2 things. One, we are doing the continuous data. We are processing over the string. 2 is we actually are allowing the query give early result. Then that means for new data comes, we have the need to refine the previous result. And okay, lastly, to do documentations. I promised to community I need to add a doc to this new style streaming. I haven't done so. I will do that. Okay, I guess that's all my presentation.